Welcome back. Today we will discuss another breakthrough in the treatment and understanding of Alzheimer's disease. You remember that in our last lecture on Alzheimer's disease we discussed the arrival of a new monoclonal antibody that had unprecedented efficacy in reducing amyloid deposits in Alzheimer's patients, and furthermore gave a first hint that this removal of amyloid deposition may actually result in an improvement in scores for dementia, such as the mini mental status. The study was not powered to show clinical differences, but it was promising, as prior trials with monoclonal antibodies had totally failed. Now today, and I think this will probably be the last breakthrough in the year 2016 in Alzheimer's disease, is a paper here that appeared in November of 2016 in Science Translational Medicine. And here in the first slide is the title. So it talks about a BACE1 inhibitor, verubicestat, MK8931. It's a Merck compound, which was developed by Merck, and I will show you in a few minutes how they went about that, reduces CNS amyloid in animal models and in Alzheimer's disease patients. So we will unpack this statement so you have a detailed understanding what this finding might mean for the future of Alzheimer's treatment and for our understanding of Alzheimer's disease. Now you recall that the amyloid deposition is the end result of a number of different events that can happen. The classical story, of course, is a genetic form of Alzheimer's disease where patients have a genetic defect or change in a variety of proteins, either the Alzheimer precursor protein itself or the so-called presenilin 1 and 2 secretases, which cut the Alzheimer's precursor protein from the membrane and liberate it into the lumen where it tends to aggregate. At least some of the species tend to aggregate. So here is a recapitulation of this, and I want to point out to you that beta secretase is in fact the enzyme BAC1 that these researchers have addressed. So this enzyme is located right here at a strategical position to cleave the precursor from the membrane, and then it liberates by the action of additional proteases a host of precursor proteins derived from the APB precursor, in particular the AP142, which tends to aggregate, and in our last lecture we dealt a great deal with the biophysics of this aggregation. So in the next slide, here's a review of the incidence of Alzheimer's disease, which is non-genetic. The genetic case is fairly easy to understand. We have a clearly defined lesion in a gene and in a protein, resulting in increased deposition of oligomers that have been aggregated and form the amyloid plaque. Now, in the elderly who do not have a genetic predisposition, what accounts for the initiation of the cascade that eventually leads to the amyloid deposition and down the road for the aggregation of the tau protein, which seems to be correlating so well with cognitive deficit in Alzheimer's disease? So here's a paper from 2012 in Nature Reviews Neurology, which proposes a sequence of events. On top here you have the normal case in which there is an equilibrium of the microglia taking care of any waste products that might be occurring in the neuron, and things are relatively stable. In step 2, now you see the beginning of inflammatory processes, as outlined in here, which begin to put stress on the neuronal system. So in aged neurons, there is the experience of chronic inflammation, and tau may become hyperphosphorylated and is missorted into somatodendritic compartments, which may impair axonal transport. So this then, in fact, puts the sequence on its head. In the lecture before, I told you that amyloid deposition is first and tau is a downstream event. Now, in this case, the authors revised the sequence of events in order to make sense of the occurrence of both tau pathology and beta amyloid deposition in patients without any genetic predisposition. Later on in this talk, I will show you a finding that again puts some doubt on this particular sequence of events. So the story is far from clear in Alzheimer's disease despite 20-25 years of intense effort. So in segment B down here, you have now stress-related accumulation of cellular protein, including the APB a precursor protein, which is cut into smaller segments and has primed microglia, which is supposed to remove these fragments and precipitated proteins from the scene. So as you see here in panel B, you begin to see the accumulation of cellular proteins which clog up the transport chain down the dendrite, and the APP is occurring here. Some lesions is present, and microglia is on the scene now, being activated by these toxic proteins and remove the perpetrators in handcuffs from the scene. Now, in the next panel, you see the further deterioration of the situation. Namely, you have the APP here in lysosomes, the axons begin to leak, and alternative processing may now occur. The microglia becomes overwhelmed and impaired, and you looking at a senile plaque here composed of fragments of the cell and the incorporated APP molecules. So that is the classical story now, as it was told in 2012 to account for late onset non-genetic Alzheimer's disease. So let's review. We have the APP protein here in the membrane inserted, a C-terminus and an N-terminus. And here's our target enzyme, BACE1, which we will discuss in a minute. So it will cleave the protein in such a way that the C-carboxyl terminal will remain within the membrane, but amyloid beta is released and forms oligomers, which apparently do all the damage. So this case is strengthened by a finding from a genetic mapping study done in Iceland. Now, Iceland has a very homogeneous genetic population, and one of the authors here, and I'll find his name right now here, Stephenson, is involved in doing detailed genetic analyses of Icelandic people, and they have discovered a mutation in the APP protein precursor gene that, rather than being predisposing to Alzheimer's disease, is in fact protective. So if you have this particular mutation, your chances of developing Alzheimer's disease are significantly reduced, namely by about 40%. And this mutation is located strategically exactly at that part of the protein where the BAC1 enzyme exerts its cleavage to cut the precursors from the membrane. So this would then strengthen the case to target this enzyme perhaps for intervention. So this compound now, the Merck compound verobicetstat, was developed and turned out to be a potent, selective, and structurally unique inhibitor of BACE1. It reduces plasma, cerebrospinal fluid, and brain concentrations of a host of AP proteins, including A beta 40, 42, and the soluble APP beta. So these are all proteins that are a direct product of the BACE1 enzymatic activity. And here was the trick. So at this day and age, we still use random screening of millions of compounds run through rapid screening machines that see whether something binds to a target protein or not. So the active domain, the active site, the catalytic site of BACE1 has been mapped at the atomic scale. So we know exactly what the pocket looks like. That does all the cutting. In fact, so we know how these scissors operate. And so the researcher came across a small molecule that binds to the pocket up here, but in a somewhat marginal fashion. It doesn't really fill out the entire pocket and is therefore a weak inhibitor of the enzyme. The researchers then harnessed the power of crystallography. In other words, having the ligand, having the small protein bind to the active site, crystallize the total complex, and by X-ray crystallography exactly map out the structure-function relationship. So now the molecule in question, the new MK compound, is here, and you can see that the motifs in compound 1 are still preserved, namely this chain here, this ring structure here, and then there is an extension to this end which maps over here into the pocket of the active site. There are a few hydrogen bonds, namely here, mapping here and here, which are still there. So we can see how detailed this is. This new compound, on theoretical grounds, was expected to be a potent inhibitor of the enzyme. So in the next slide, we now see the binding constants, the affinity with which this compound binds to the different forms of the enzyme. So here is the classical human BACE1, and the binding constant is in the nanomolar range. Now, nanomolar is where the action is. Nanomolar implies high affinity. Now, other similar proteins or peptidases have much lower affinity, as indicated by the astronomical numbers over here. Now, these are just some cell lines which express the AP precursor protein, which also have a fairly substantial binding ability. But the number to focus on is, of course, this. The next slide is still a reminder here where the action is. You remember the beta secretase, which is identical to BACE1. So that's where all the action is. If we can stop this enzyme, we may be able to stop all this downstream cascade. The next slide. The single and multiple doses they found were well tolerated and produced reductions in A beta 40, 42, and the soluble form in the spinal fluid of both healthy Norman subjects and Alzheimer's patients. And here you see the results. This is immunoreactivity of the AB40. And interestingly, there is an increase in normal controls. This is a common finding in folks who have an indwelling catheter in their intrathecal space, basically accessing the fluids around the brain. So this is not a evolution of Alzheimer's pathology in 36 days. Rather, it's a normal side effect of an indwelling catheter. But you can see that different doses of the compound that we're discussing lead to a significant decrease in the accumulation of these A-beta fragments. Next slide. So because of this favorable findings and the initial preclinical findings, there are now a number of clinical trials going on, and the compound has graduated from phase 2 to phase 3. Now that is kind of the critical step. Phase 1 in clinical trials is just a basic safety study. Phase 2 is a proof of concept in a small number of patients, and phase 3 is where you go to town to really show differences in disease progression, difference from normal controls to patients with Alzheimer's disease, etc. So you need positive trials in phase 3 to get approval from the FDA that your compound is worth anything. Now we don't know what degree of A-beta reduction or amyloid reduction is necessary to produce cognitive improvement. And that's one of the problem that this group is wrestling with. It depends on which dose to choose and which degree of elimination of beta amyloid you want to shoot for to hope to maximize the reduction of progression or the reduction in cognitive decline. The next slide. And because the deposition of amyloid plaques begins years before Alzheimer's diagnosis is made, we don't know when to initiate treatment. And that's one of the big problems in Alzheimer's disease. We are in a quandary. So here is the other paper that is kind of in tandem with our anchor paper that we're discussing today. And it's targeting the relationship between the production of tau and the appearance of the peptides that we discussed produced as a result of BACE1 action. So these investigators knocked out BACE1 in animal models and then looked at what happens to tau. What is the relationship, in fact, between APB accumulation and the appearance of tau? On the next slide, I show you the progression or the dissociation, really, between the amyloid reactivity in the brain, here on this axis, and the appearance of symptoms on this axis. So this is normal cognition over here. Now, as immunoreactivity of amyloid increases in the brain, people tend to report subjectively some decrease in memory, recalling names and other mild symptoms of perhaps mild cognitive impairment. Now, mild cognitive impairment is a direct precursor of later dementia, and as shown here, you can see that the deposition of amyloid correlates with the appearance of mild cognitive impairment after a significant time delay. So here you already have accumulated amyloid, but no mild cognitive impairment. So there's a dissociation. Next slide. We see it in much more detail. So here we see the AP amyloid appearing early in the story and increasing over time. Now, CSF tau appears later. Still, no clinical effects are really visible. If you take people off the street of a certain age, you do MRI or glucose PET scanning to look at their metabolic activity, you can see that things begin to happen. Things begin to go wrong in the brain, yet cognitively the patient is still normal. And only after an extended length of time does the cognitive problem catch up. Patients at low risk with good cognitive reserve and the lack of other risk factors such as diabetes, obesity, brain trauma, etc., have a long delay until cognitive impairment appears, although the other biomarkers already have been positive for many years or perhaps some decades in advance. If you're at a high-risk group, your cognitive impairment will show up much earlier. And this differential in time may be extremely important. If we can maximize our intervention in high risk factors, we may delay the onset of cognitive impairment for so many years that patients die of other causes before succumbing to the ravages of Alzheimer's disease. So here now is the finding. In experimental animals that had their BACE1 blocked, tau did just not appear. Here in this animal model, tau slowly accumulated as a function of age of the experimental animal. So here are mice that do not have the transgene, and you can see that tau levels are kind of randomly all over the place, but don't show the typical increase that you see here. So this would suggest that by knocking out the peptidase, the BACE1, early in the game, you may be able to prevent the aggregation and the occurrence of tau. Now this is in contrast to the model I showed you at the beginning that attempted to explain sporadic Alzheimer's disease in some early occurrence of tau, leading to microtubule problems, problems in transport through the neuron, and the subsequent appearance of amyloid plaques as a consequence of tau pathology. So that does not appear to be the case, at least in this animal model of Alzheimer's disease. So here then you see the increase as a function of age of brain AP, and here you see human AP and tau, and you see the perfect correlation of the occurrence of the AP peptide and the tau tau protein that supposedly drives the destructive pathology, leading to neuronal death. So this is then the experiment. Mice were either given a control diet or being fed the BACE1 inhibitor, and the brains were subsequently examined. And you can see here that by looking in a stereological quantification at neocortical A-beta staining, you can see that in the control animal, you can see that A-beta is increasing, and if you block the enzyme, there's a dramatic reduction here occurring. So then that would indicate that this is a very powerful approach to curtail and to basically nip in the bud the possibility that in this transgenic mouse which is predisposed to developing Alzheimer's disease, you can block the progression of the disease by early intervention, shutting down the BACE1 enzyme. And here is another presentation of this. You can see now the tau pathology, which is also shut down by the enzyme after 7 months. Usually the mouse is beginning to show Alzheimer's pathology, but by blocking BACE1, you not only prevent the AP precipitation, but you also prevent the tau pathology. So that is rather stunning and very promising. So tau may be going in tandem with amyloid being the primary culprit and the prime offender. And if intervention can be targeted right there and then, tau pathology perhaps could be eliminated and prevented. So these were two papers appearing 1 month apart late in 2016. And I believe that both papers will make the top 10, the hits in 2016. We will have a presentation on the top 10 most dramatic and stunning findings in neuroscience in the year 2016, in which we will review and rank what we believe subjectively to be the greatest breakthroughs. I believe one is the recent findings on schizophrenia genetics, and I believe that 1 or 2 of these papers will also make the top 10 list. So we look forward to seeing you then for this end of the year New Year celebration in neuroscience. Thank you.